There is a moon in our solar system that should not exist. Not in the way it does, anyway. It has rivers, it has lakes, it has rain, clouds, seasons, and a thick orange atmosphere that blocks out the sun and turns the sky into a permanent hazy twilight. It has mountains and valleys and vast flat plains that stretch for hundreds of kilometers. If you were to stand on its surface, the air pressure would feel roughly like standing 10 meters underwater in an ocean. You could almost breathe it, almost. This moon is called Titan, and it orbits Saturn. And here is the thing that will keep you up at night once you really understand it. We have known about Titan's extraordinary nature for decades. We have known that it is the most Earth-like world in the entire solar system. We have known that it has liquid on its surface, that it has weather systems, that its chemistry is so complex it borders on the kinds of chemistry that, on Earth, we associate with the beginning of life. We have known all of this, and in all that time, in all those decades, we have never once landed a probe on its surface and kept it running for long enough to answer the questions that matter most. NASA has sent one lander to the surface of Titan, just one, and it lasted about 72 minutes before it went silent. 72 minutes on the most interesting moon in the solar system, and then nothing. No follow-up mission, no second attempt, no surface rover crawling along the shores of its methane lakes. And when you start asking why, when you start digging into the documents and the internal assessments and the mission proposals that have been written and rewritten and shuffled around for 20 years, you find something strange. The most detailed explanation NASA has ever produced for why a sustained Titan surface mission is so technically difficult is contained in a document that, to this day, carries a sensitive but unclassified designation. It is not secret, it is technically available. But it is not easy to find, it is not publicized, and almost nobody outside of the aerospace engineering community has ever read it or even knows it exists. And that document tells a story about Titan that is far more complicated, far more challenging, and in some ways far more unsettling than anything you have ever been told about this moon. So let's start from the beginning. Let's start with what Titan actually is. Because most people think they know, and most people are only about halfway there. If you want to subscribe to this channel, now is a good time to do that. Because we are going deep into one of the strangest places in the solar system, and this is only the first stop. Titan was discovered in 1655 by a Dutch astronomer named Christian Huygens. He was looking at Saturn through a fairly primitive telescope and noticed a small, bright dot that moved around the planet in a consistent way. He correctly identified it as a moon. At the time, that was the entire extent of what anyone could know. It was a point of light, nothing more. For the next 300 years, Titan was just that, a point of light, a name in a catalog, one of Saturn's many moons, slightly larger than the others but otherwise unremarkable from a distance. Then, in 1944, a Spanish-born American astronomer named Gerard Kuiper did something remarkable. Using a new spectrographic technique that allowed scientists to analyze the chemical composition of distant objects by studying the light they reflect, Kuiper pointed his instruments at Titan and found something no other moon in the solar system had ever shown before. He found an atmosphere. Not just a thin wisp of gas clinging to the surface the way some moons have trace atmospheres, a real, dense, substantial atmosphere, the kind you could measure, the kind with actual chemical signatures, and the dominant signature Kuiper found was methane. Now, methane is a molecule. It is one carbon atom bonded to 4 hydrogen atoms. On Earth, it is produced by biological processes, by decomposing organic material, by the digestive systems of living creatures, by swamps and marshes and rice paddies. Finding it in the atmosphere of another world set off alarm bells in the scientific community that have never fully gone quiet. At that point, nobody could say anything definitive. There was not enough data. But the idea that Titan might be a world worth investigating intensely was planted right there in 1944, and it has been growing ever since. The first spacecraft to get a close look at Titan was Pioneer 11, which flew past Saturn in 1979. It could not see through the atmosphere. The orange haze that covers Titan is not just a thin cloud layer. It is a thick, opaque photochemical smog that extends hundreds of kilometers above the surface and completely blocks visible light from getting through to the ground. Pioneer 11 saw the same thing that Huygens saw 300 years earlier, an orange ball, featureless and impenetrable. Then came Voyager 1 in 1980, and this is where the story starts to get genuinely strange. Voyager 1 was supposed to continue its tour of the outer solar system after visiting Saturn. It was supposed to keep going, the way Voyager 2 did, visiting Uranus and Neptune. But NASA made a decision. They changed the trajectory of Voyager 1 specifically to get a closer look at Titan. And the reason they did that is because by 1980, scientists already suspected that what was hiding under that orange atmosphere might be unlike anything else in the known solar system. The cost of that decision was enormous. By flying close to Titan, Voyager 1 was flung out of the plane of the solar system on a trajectory that meant it could never visit another planet again. NASA essentially sacrificed Voyager 1's planetary science mission to get a better look at Titan. What did they find? Voyager 1 confirmed what Kuiper had detected: a thick nitrogen atmosphere, about 1.5 times the pressure of Earth's atmosphere at sea level, loaded with methane and complex organic molecules called tholins. These tholins are what give Titan its distinctive orange color. They form when ultraviolet light from the sun interacts with methane and nitrogen in the upper atmosphere and creates long chains of carbon-based molecules that rain down slowly onto the surface. The surface temperature on Titan is around -179 degrees Celsius. At that temperature, water is not a liquid. Water ice on Titan is as hard as rock, but methane and its chemical cousin ethane can exist as liquids at that temperature, which means that on Titan, the lakes and rivers and rain and clouds are not made of water. They are made of liquid methane and ethane. And this is where everything gets philosophically complicated. On Earth, we think of water as the essential ingredient for life. Water is the solvent. Water is what chemistry happens inside of. Water is why we look for wet worlds when we search for places that might support biology. But Titan makes you ask a different question. Is water the only solvent that works? Or is it just the one that works here, at Earth's temperature, at Earth's pressure? Some chemists believe that in a methane-based solvent at cryogenic temperatures, completely different kinds of chemistry might be possible. Chemistry that does not look anything like Earth biology. Chemistry that we do not have the tools to recognize or understand yet. There are theoretical models of cell membrane analogs made of nitrogen-containing organic molecules that could function in liquid methane the way phospholipid bilayers function in liquid water. We have never found one, but we have never looked properly either. And that is the maddening thing about Titan. Every single time we get new data, every single time we manage to observe it in more detail, the evidence that something chemically interesting is happening on and just below its surface gets stronger. And yet we have never gone back with anything capable of spending real time there. The most important mission to Titan so far was the Cassini-Huygens mission. Cassini was a joint project between NASA, the European Space Agency, and the Italian Space Agency. The spacecraft launched in 1997 and arrived at Saturn in 2004. It was enormous, the size of a school bus, and it carried with it a separate probe named Huygens, built by the European Space Agency, specifically designed to enter Titan's atmosphere and descend to the surface. Cassini spent 13 years orbiting Saturn and performing over 100 flybys of Titan. During those flybys, it used radar to punch through the opaque atmosphere and map the surface. What it revealed was staggering. The northern hemisphere of Titan is covered with hundreds of lakes and seas filled with liquid methane and ethane. The largest of these, called Kraken Mare, is larger than all of the Great Lakes of North America combined. There is another large sea called Ligeia Mare and another called Punga Mare. These are not small features. These are massive bodies of liquid sitting on the surface of another world. The equatorial regions of Titan are covered with enormous dunes. Not sand dunes the way we think of on Earth, but dunes made of organic particles, the tholins that rain down from the sky, sculpted by winds into ridges and waves that stretch for hundreds of kilometers. And then there are the impact craters, or rather, the notable absence of them. Titan has very few impact craters compared to most solid bodies in the solar system. This tells scientists something important. The surface is geologically young. Something is resurfacing it. Whether that is cryovolcanism, which is essentially ice volcanoes that belch out water and ammonia, or whether it is erosion from rain and rivers, or some combination of both, Titan's surface is actively being renewed. It is a dynamic, living geology, which is extraordinarily rare in the outer solar system. Then, in January 2005, the Huygens probe did something that had never been done before and has not been done since. It entered Titan's atmosphere, slowed itself with parachutes over the course of about 2.5 hours, and landed on the surface. The images it sent back are still some of the most haunting in the history of space exploration. During the descent, Huygens took photographs of the landscape below. You can see what look like river channels carved into higher ground, leading down toward a flatter, darker lowland area. The channels are the same shape as drainage networks on Earth. They look like riverbeds. They look like something liquid flowed through them and carved them out over a very long time. When Huygens reached the surface, it landed on something that the scientists described as being like wet sand or clay. The surface yielded slightly under the probe's impact, the way soft ground does, and the soil around the landing site was littered with small, rounded pebbles made of water ice. Rounded, the way river rocks get rounded. Rounded by being tumbled and rolled and smoothed by flowing liquid. The probe was designed to send data back to Cassini overhead, which would then relay it to Earth. And it worked. For 72 minutes, Huygens transmitted from the surface temperature, atmospheric composition, wind data, images, and then Cassini moved past the horizon, the relay link was broken, and the transmission ended. Huygens was still on the surface, still functional as far as anyone knew, but there was nothing left overhead to listen to it. 72 minutes. That is all we have from the surface of the most interesting moon in the solar system. Now here is where things start to get complicated. After Cassini-Huygens, you would think the obvious next step is obvious. Send something back. Send a surface mission. Send a rover. Send a long-duration lander. This is a world that has rivers and lakes and complex chemistry and a thick protective atmosphere. It is one of the top candidates for potentially harboring some form of life in the entire solar system. You send something back as quickly as you can. Except you do not. Almost 2 decades have passed since Huygens landed, and nothing has gone back. Why? The simple answer people give is money and priorities. Space exploration is expensive. Mars gets the funding because Mars is closer, and humans might go there someday, and there is a compelling political and public narrative around humans on Mars. The outer solar system gets comparatively little attention. But that is not the complete answer. That is the polite, press release answer. The real answer is technical. And the real answer is contained in those documents that aerospace engineers write for each other, not for the public. Here is what those documents say. Landing on Titan and keeping something alive and functional for a meaningful period of time is one of the most technically complex challenges in the history of space exploration. Not because the landing itself is hard. The thick atmosphere actually makes landing relatively easy compared to somewhere like the Moon or Mars. A parachute works beautifully in Titan's atmosphere. The pressure is high enough and the gravity is low enough, about 1/7 of Earth's gravity, that you could theoretically float something down gently and have it land without any retrorocket system at all. The problem is not getting there. The problem is surviving once you arrive. Let's talk about power. Every spacecraft that lands on another body needs a power source. For Mars rovers, solar panels work because Mars is close enough to the sun that sunlight, even at Mars's distance, provides usable energy. But Titan is 10 times farther from the sun than Earth is. The sunlight that reaches Titan is about 1% of what reaches Earth, and even that tiny fraction has to fight its way through the thick orange smog of the atmosphere before it gets to any solar panels on the surface. The practical power output from solar panels on Titan's surface would be essentially negligible. Solar power does not work on Titan. The only realistic power source for a long-duration Titan surface mission is a radioisotope thermoelectric generator, an RTG. This is the same kind of power system that Cassini used, that the Voyager probes used, that Curiosity uses. It works by converting the heat produced by the natural radioactive decay of plutonium-238 into electricity. It requires no sunlight. It just runs, quietly and reliably for decades. But plutonium-238 is extraordinarily expensive and in very short supply. The United States stopped producing it in the 1980s. For years, the only source was Russia, and that relationship has been complicated. The Department of Energy restarted domestic production in the early 2010s, but the production rate is slow. There is simply not enough plutonium-238 to power every mission that wants to use it. And allocating what little exists is a significant constraint on what missions can actually be built and flown. So you have a power problem. That alone makes a Titan surface mission vastly more expensive and logistically difficult than a Mars mission. But the power problem is actually not the hardest problem. The hardest problem is the temperature, minus 179 degrees Celsius. That is the temperature at Titan's surface. That is not just cold. That is an engineering nightmare of the highest order. Every electronic component, every battery, every mechanical part, every sensor, every camera, every transmitter on a spacecraft is designed to operate within a certain temperature range. Most commercial electronics fail somewhere below minus 40 degrees. Even aerospace-grade components, built specifically for space applications, typically have operational limits around minus 120 degrees Celsius. Titan's surface temperature is 60 degrees colder than that. At minus 179 degrees, lubricants freeze solid. Mechanical joints seize up. Electronic components lose their ability to function. Battery chemistry fails. Even the materials that make up the structure of the spacecraft begin to behave differently at that temperature, becoming brittle in ways that make structural failures more likely. You can insulate against the cold. You can build a heated enclosure that keeps the electronics warm using waste heat from the RTG, and that works, to some extent. Huygens was designed this way and it survived its brief time on the surface. But keeping something warm enough to function while also keeping it light enough to be launchable, while also managing the power budget, while also building it to survive for months or years rather than minutes, is a set of engineering requirements that pull in contradictory directions simultaneously. Making the insulation better adds mass. Adding mass requires more fuel to get there. More fuel means a heavier spacecraft. A heavier spacecraft needs a bigger rocket. A bigger rocket costs more money. And at every step of that chain, the cost increases not linearly but exponentially. But wait, because it gets more complicated still. The other side of the thermal problem is not keeping things warm, it is keeping things cool. The RTG that powers your spacecraft also produces heat. Lots of it. A typical RTG produces several hundred watts of thermal energy and only converts a small fraction of that into electricity. The rest is waste heat. On most spacecraft, that waste heat radiates into the cold vacuum of space, simple and effective. But on Titan, the thick atmosphere changes everything. Titan's atmosphere is not a vacuum. It conducts heat. It insulates. The atmosphere essentially acts as a blanket around your spacecraft, trapping the waste heat from the RTG and preventing it from dissipating properly. This means that even though the external environment is extraordinarily cold, the spacecraft itself can overheat if the thermal management system is not designed extremely carefully. You are simultaneously trying to keep your electronics warm enough to function in the external cold, while also preventing your RTG's waste heat from cooking your electronics from the inside. You need thermal management systems that can handle both extremes at the same time, dynamically adjusting based on whether a given component is at risk of freezing or overheating. And those systems are heavy, and complex, and expensive, and they can fail. There is a term that engineers use for this situation. They call it a thermal environment unlike anything else in the solar system. And the documents that discuss this in detail, the internal NASA assessments and contractor studies, use language that is unusually direct about how difficult this problem is to solve. These are not documents that minimize challenges. They are documents written by people who have spent careers understanding how things fail in space, and they do not mince words. Now let's talk about communications. Getting data back from Titan is slow. Titan is on average about 1,200,000,000 kilometers from Earth. At that distance, Radio signals traveling at the speed of light take between 67 and 90 minutes to make the one-way trip, depending on where Saturn is in its orbit relative to Earth. You send a command. An hour and a half later it arrives. Another hour and a half before you see the response. This is not unique to Titan. Every outer solar system mission deals with this. But the bandwidth, the amount of data you can actually transmit per second, is constrained by the distance. The signal weakens with the square of the distance. Titan is roughly 10 times farther from Earth than Mars is. A radio signal that carries 1 unit of data per second from Mars would carry only 1/100th of that data per second from Titan, assuming the same transmitter power and antenna size. Getting high-resolution images and scientific data back from a Titan surface lander in real time is not possible. You send compressed bursts of data during communication windows and you wait. This is manageable. But it means that the lander needs to be extremely autonomous. It needs to be smart enough to make decisions on its own, without waiting for instructions from Earth. It needs to be able to detect problems and respond to them without a human in the loop. That requires sophisticated onboard computing systems, which adds mass and cost and potential failure modes. And then there is the question of the liquid methane lakes. This is where the story gets philosophically interesting again, and where the internal discussions at NASA have been most pointed. The lakes and seas of Titan are arguably the single most scientifically compelling target in the solar system for astrobiology research. If any form of life exists in the outer solar system, the methane lakes of Titan's northern hemisphere are one of the most plausible places to look. The chemistry in those lakes is extraordinarily complex. The organic molecules raining down from the atmosphere dissolve into the liquid methane and ethane and interact in ways we do not fully understand. There may be dissolved compounds, gradients of chemical concentration, interfaces between the liquid and the lakebed, all of the kinds of complexity that chemists associate with environments where interesting things happen. A surface lander that stays on dry land tells you a great deal, but a surface lander that can sample the liquid directly, that can analyze the chemistry of a Titan lake, that can look for structures or gradients or signatures that might indicate biology, that is the mission scientists have been dreaming about for 40 years. But landing in or near a lake on Titan is vastly more complicated than landing on solid ground. You need to know exactly what the shoreline looks like. You need to know the depth and viscosity of the liquid. You need to know what the lakebed is made of. You need to know whether the liquid is calm or turbulent, whether there are currents, whether the composition varies by depth or location. And you need to land accurately enough to get where you want to be without ending up in the middle of a methane sea with no way to take useful samples, or on a shoreline that turns out to be too soft to support your spacecraft. We do not have good enough maps of Titan's surface to land precisely. The radar data from Cassini gave us a general picture, but the resolution is not sufficient to pick a safe landing site with confidence. Before you can land a science mission on the shores of a Titan lake, you probably need another orbital mission to map the surface in much higher resolution, which means another mission before the mission, which means more time, more money, more complexity. This is a pattern that repeats throughout the history of outer solar system exploration. Every good answer raises 3 new questions that need to be answered before you can take the next step. The solar system is generous with its mysteries and stingy with its solutions. Now, about that document. I want to be careful here about how I describe this, because precision matters. What I am describing is not a single smoking gun document that reveals a conspiracy or a cover-up. It is something more mundane and in some ways more interesting than that. It is a technical assessment, a serious, detailed engineering study of the challenges of a long-duration Titan surface mission, prepared by NASA contractors and reviewed internally, that lays out in very frank language exactly how hard this problem is and what the current state-of-the-art in technology can and cannot do. The sensitive but unclassified designation exists not because of any national security implication, but because documents of this type sometimes contain proprietary technical information from contractors, or contain frank assessments of failure modes and system vulnerabilities that the agencies involved prefer not to publicize broadly, not out of malice, but because engineering documents written for internal audiences are not written in the same diplomatic language as press releases. They say things like, "This system will fail under these conditions, and we do not currently have a solution," which reads very differently in a headline than it does in a technical review. The contents of this kind of document, and there are several versions of it from different years and different study groups, paint a picture of a mission that is not impossible, but that requires technological advances we do not yet have, deployed at a cost that has consistently exceeded what any mission budget could accommodate within a reasonable planning horizon. What those assessments identify, repeatedly, across multiple study iterations, is a cluster of core technical challenges that all need to be solved simultaneously, not sequentially, simultaneously. Improving your RTG does not help you if you still cannot solve the thermal management problem. Solving the thermal management problem does not help you if you still do not have a communications architecture that can support the data volume you need. Solving the communications problem does not help you if you still cannot land accurately enough to reach your science targets. These problems are coupled. Progress on one does not automatically produce progress on the others. And the funding environment for the outer solar system has never been generous enough to run all of these technology development programs in parallel at the speed required to make a flagship Titan surface mission feasible within the timeframes that mission planners need to work within. Now, here is something that most people do not know. NASA actually selected a Titan mission. It selected one, and it is in development right now. It is called Dragonfly, and it is extraordinary. Dragonfly is not a lander in the traditional sense. It is a rotorcraft lander. It is essentially a large drone, a multi-rotor flying vehicle roughly the size of a car, designed to fly through Titan's atmosphere, land, take samples, analyze them with onboard instruments, and then fly to a completely new location and do it again. It leverages the fact that Titan's thick atmosphere and low gravity create conditions that are actually quite favorable for rotorcraft flight. The same thick air that makes thermal management so difficult also makes it relatively easy to generate lift. Dragonfly would use its 8 rotors to hop across Titan's surface, covering more ground in a single mission than all of the Mars rovers combined. The mission was selected in 2019 as part of NASA's New Frontiers program. It is currently planned to launch in 2028 and arrive at Titan in 2034. It would land in the equatorial dune fields, an area of relatively flat terrain where the tholins from the atmosphere have accumulated and where the organic chemistry is expected to be extremely rich. Over the course of its nominal mission, it would fly hundreds of kilometers, visiting multiple sites, including eventually a site near a dried, ancient impact crater where water and ammonia from Titan's interior may have mixed with the surface organics to create a temporary liquid water environment billions of years ago. And here is the thing about Dragonfly that nobody talks about enough. It is explicitly designed to look for the chemical signatures of life, or of prebiotic chemistry, the chemistry that comes just before life. It carries a mass spectrometer that can analyze the composition of surface materials at the molecular level. It carries meteorological sensors. It carries cameras. It carries a seismometer. It is a genuinely powerful science platform, not just a technology demonstration. But Dragonfly also illustrates perfectly why it has taken this long to get here. The reason Dragonfly works as a concept where previous lander concepts have struggled is because it is specifically designed around the unique properties of Titan's environment rather than trying to fight against them. Previous lander designs tried to adapt existing Mars lander architectures to Titan's conditions. They assumed a stationary or slow-moving surface vehicle. They assumed solar power supplemented by battery. They assumed relatively conventional communication systems. And in every case, when engineers ran the numbers, they ended up with something that was too heavy, too power-hungry, too expensive, or too fragile to survive long enough to do meaningful science. Dragonfly solves the power problem by using an RTG. It solves the thermal management problem with a carefully designed warm electronics box that keeps the critical systems within their operational temperature range. It solves the mobility problem by flying rather than rolling, which means it does not need to navigate around rocks or cross difficult terrain with wheels. And it solves the communication problem by using Cassini's legacy data to plan its flights carefully and transmit data in efficient compressed bursts during windows, when Earth is in the right geometry to receive it. None of these solutions are simple. Every one of them required years of engineering development. The rotors alone, blades that can spin fast enough to provide lift in Titan's cold, dense atmosphere, while being built from materials that do not shatter at cryogenic temperatures, represent a substantial materials science achievement. There is no off-the-shelf blade you can use. You have to design and test one from scratch, at temperatures that require cryogenic test chambers that are themselves not common pieces of equipment. The power system requires plutonium-238 that has to be produced, processed, and encapsulated safely. The warm electronics box requires insulation materials and heaters that add mass at every iteration and have to be balanced against the weight budget of a vehicle that needs to be light enough to actually fly. And the entire thing has to survive an 8-year cruise to Saturn, survive the radiation environment of the outer solar system, survive entry into Titan's atmosphere, survive landing, and then survive on the surface for a nominal mission of about 3 years, potentially longer if the RTG holds up and the mission is extended. All of this explains the timeline. Dragonfly was not a mission that could have been flown in 2010 or 2005. The technology needed to build it did not exist. The materials science was not mature enough. The RTG production capacity was not there. The computational power required for the autonomous navigation systems was not available in a form light and efficient enough to carry on a flying spacecraft. Everything that makes Dragonfly possible has been developing in parallel over the past 2 decades, and it has only recently reached the point where the mission is technically feasible within a budget that a space agency can actually approve. This is what those internal documents understood years before the public did. The scientists knew what they wanted to find on Titan, the engineers knew what it would take to get there, and the gap between what science wanted and what technology could deliver was large enough that even the most optimistic projections put a real Titan surface mission decades in the future. The documents that described this gap in the clearest terms were not publicized because nobody in the agency wanted to explain to the public and to Congress why one of the most exciting targets in the solar system was going to have to wait a generation. There is another dimension to this story that deserves attention, and it is the one that tends to make scientists the most uncomfortable when you bring it up. Planetary protection. NASA has a set of guidelines called Planetary Protection Policies that govern how spacecraft are designed and operated to prevent contaminating other worlds with Earth biology, and to prevent bringing potentially harmful biological agents back to Earth. For Mars, these policies are strict. For the outer solar system ice moons like Europa and Enceladus, which might have liquid water oceans where Earth-type biology could potentially survive, the policies are extremely strict. For Titan, the planetary protection designation has historically been relatively relaxed. This is because scientists assumed that Titan's extreme cold made it unlikely that Earth microorganisms, even the toughest extremophiles we know of, could survive and reproduce there. At -179 degrees Celsius, the biochemical reactions that life as we know it requires simply cannot happen. But here is the complication. We do not fully understand the chemistry of Titan. If there is life on Titan, it is not life as we know it. It might be chemistry that functions in liquid methane. It might be completely unlike anything in our biological textbooks. And that means that when we think about contamination risk, we cannot simply apply the rules we use for places where water-based life might exist. If we land a spacecraft on Titan and there is exotic chemistry happening there that we do not understand, we run the risk of introducing Earth compounds, even trace compounds from manufacturing residues on our spacecraft surfaces, that could interact with that chemistry in ways we cannot predict. We might destroy the very thing we are looking for before we have a chance to recognize it. And conversely, if there are exotic organic compounds on Titan, complex enough to be considered precursors to some form of life, there is a non-zero discussion, not a mainstream concern but a discussion, about what happens if those compounds come back to Earth someday on a sample return mission. Dragonfly is not a sample return mission. It will not bring anything back to Earth, but the fact that these discussions are happening at all reflects how seriously some scientists take the possibility that Titan's chemistry is genuinely extraordinary. And that seriousness is what connects all of these threads: the funding challenges, the technical difficulties, the internal documents, the long gaps between missions. At the root of all of it is a simple fact that the scientific community has understood for decades and that the general public has barely begun to appreciate. Titan might be the most important place in the solar system, not because it is the most likely place to find life. Mars is probably higher on that list, and Europa's ocean is a strong contender. But because of what Titan represents theoretically, Titan is a laboratory for prebiotic chemistry. It is a world where the raw ingredients of life, the complex organic molecules, the nitrogen-rich compounds, the reactive chemistry, have been cooking for 4.5 billion years. Whatever is happening in those lakes and dunes and rivers has been going on since the solar system formed. Titan is not just interesting as a place where life might exist today. It is interesting as a record of what chemistry can do when given enough time and enough ingredients and left alone to run. If we go to Titan and find nothing alive, we will learn something profound about how rare life really is. If we go to Titan and find something alive, or something that looks like it was recently alive, or something that looks like it is trying to become alive in some way we have never imagined, that will be the most important discovery in the history of science. Either outcome is worth every dollar and every year of engineering development it takes to get there. And that is what makes the long wait so frustrating. Every year that passes without new data from Titan is a year of ignorance about one of the fundamental questions of existence. Are we alone? Is life an inevitable consequence of chemistry given the right conditions? Or is Earth an accident, a fluke, a 1 in 100 billion shot that happened to hit? Titan has information that bears on those questions directly, and for 20 years, we have had 72 minutes of surface data to work with. Let me tell you about some of the things those 72 minutes revealed, because even in that brief window, Huygens found things that have driven 2 decades of scientific discussion. During its descent, Huygens detected a strong spike in methane concentration near the surface. This spike was unexpected. The models predicted a relatively uniform distribution of methane throughout the lower atmosphere. What Huygens found instead suggested that there was a localized source of methane near or at the surface, something that was releasing or evaporating methane from the ground. The most obvious interpretation is that Huygens landed near a region where liquid methane was present just below the surface, saturating the ground the way moisture saturates wet soil, and that the heat from the probe itself was evaporating it. This is significant because it tells us that liquid methane is not just sitting in visible lakes and rivers in certain regions of Titan. It may be present in the subsurface across much wider areas, the way groundwater is present beneath the surface on Earth, even in regions that look dry from above. During its final approach, Huygens also detected what appeared to be a dry riverbed that had recently, in geological terms, carried liquid. The rounded pebbles at the landing site, which were confirmed to be water ice, showed the characteristic smoothing of fluvial transport. They had been in a flowing liquid long enough to have their sharp edges worn away. This is not ancient geology. The river systems on Titan appear to be active on timescales of tens of thousands of years, possibly much shorter. And the surface itself, that wet sand consistency, the slight yielding on impact, suggests a surface that is not solid bedrock, but rather a layer of granular organic material, the tholins raining down from the sky, accumulating, compacting, and creating a soft substrate that behaves somewhat like soil. In some regions of Titan, this organic soil layer could be meters deep, representing billions of years of atmospheric chemistry literally raining down and piling up on the ground. This is not a dead world. This is not a frozen, inert rock floating around Saturn. This is a world in motion, a world with weather and erosion and chemistry and change, a world that, if you squinted and tried not to think about the temperature, would feel in some ways more familiar than Mars. Mars is a world that was once alive with geology, and perhaps with liquid water, and has since died. Mars's atmosphere is thin and cold and offers little protection. Its surface is bombarded with radiation. Its chemistry is relatively simple. Mars was interesting once, and we are trying to understand what happened to it. Titan is interesting now. Whatever is happening in its chemistry is happening right now, on a world that has been geologically active and atmospherically complex for 4.5 billion years. There has been no planetary catastrophe, no massive atmospheric loss event, no magnetic field failure. Titan has just been steadily cooking its chemistry, year after year, epoch after epoch, since the solar system formed. 4.5 billion years is a very long time. Life on Earth got started within the first billion years after the planet formed. If the chemistry of life can begin within a billion years given the right conditions, and if Titan's chemistry is even remotely in the right neighborhood, then we have had more than enough time. Of course, temperature matters. Chemistry at -179 degrees happens slowly. The reaction rates for organic chemistry in liquid methane are orders of magnitude slower than they are in liquid water at room temperature. What might take a year at Earth temperatures could take 10,000 years on Titan. 4.5 billion years might be equivalent, in chemical terms, to only a few 100 million years of Earth chemistry. But a few 100 million years was enough on Earth. Nobody is claiming that Titan definitely has life. The scientists who study it are careful and precise about this. What they say is that Titan's chemistry is far too interesting to write off without a serious, sustained investigation. What they say is that the data we have raises questions that demand better answers. What they say is that the 72 minutes Huygens spent on the surface was a tantalizingly brief look through a keyhole into a room that might contain something extraordinary. Dragonfly will open that door. If everything goes to plan, if the budget holds, if the launch window in 2028 is met, if the 8-year cruise proceeds without incident, if the entry and descent and landing work correctly, if the rotors perform as designed in the cold, dense air, if the RTG produces the expected power, if the warm electronics box keeps everything within its operational temperature range, there are a lot of ifs. Space is hard. The outer solar system is harder. Titan is hardest of all. But Dragonfly represents something important beyond its scientific objectives. It represents the moment when all of the technology development, all of the engineering studies, all of the documents written for internal audiences, all of the frustrating decades of knowing what was there, but not being able to reach it properly, finally converged into something that can actually be built and flown. This is how space exploration actually works. Not the way it looks in movies, with heroic decisions made in dramatic moments by visionary leaders. It works slowly. It works through decades of patient engineering. It works through internal documents that say bluntly what the press releases cannot say. It works through scientists spending careers on problems that will not be solved within their lifetimes. And it works through the accumulation of small technical achievements that each individually seem modest, but collectively make the impossible merely difficult. The story of why we have never put a proper lander on Titan is not a story of negligence or conspiracy or misplaced priorities, although budgetary priorities have certainly played a role. It is a story about the physics and engineering realities of one of the most extreme environments in the solar system. It is a story about what it actually takes to visit a world that is cold enough to freeze your electronics, dark enough that solar panels are useless, thick-aired enough that thermal management becomes a three-dimensional puzzle, and distant enough that every gram of mass and every watt of power has to be fought for. It is, in other words, a story about how hard the solar system is when you take it seriously. And it is a story that, if Dragonfly succeeds, will have an ending worth waiting for. Because when that rotorcraft sets down for the first time in the organic dunes of Titan's equatorial region, when it spins up its rotors and lifts off and flies toward its first science target, when it dips its instruments into the chemistry of a world that has been waiting 4.5 billion years to be examined properly, we will either find confirmation that the chemistry of life is unique to Earth,